Today's topic of revision is dual nature of radiation and matter. Okay, so what exactly is the radiation? Let's first talk about that. When we say radiation, we mean electromagnetic radiation. And when we say matter, by matter we mean particles. They may be subatomic particles like electrons or atoms, or even macroscopic bodies like humans. Macroscopic. Okay, now what is meant by dual nature? Okay, what is meant by dual nature? Just before discussing dual nature of radiation and matter, we have talked about electromagnetic waves and wave nature of light. So that is what we expect. Okay, wave nature here. And when we talk about this, okay, we expect these to be particles. But then by dual nature we mean matter exhibits wave-like nature in some cases or under some conditions, and electromagnetic radiation exhibits particle nature in some circumstances. That is exactly what is the essence of this chapter, dual nature of radiation and matter. Have you understood this? Okay. Now to begin with, let us discuss photoelectric effect, which is an indicator that electromagnetic radiation behaves as a particle, and we give a name to that particle, we call it a photon. So what exactly is a photon? What led to the introduction of such a concept of photon by Einstein and Max Planck? We will now revise it quickly. Acha. So we will start with metals. So we all know that even in current electricity we have discussed this, that metals have a very large number of free electrons. Metals have very large number of free electrons. What exactly do we mean by that? Can we pick the electrons out from the metal with our hands? No. Okay. These electrons are still bound to the metal lattice, but the thing is they are free to roam anywhere inside. It's like a bunch of children who are there wandering in a small room, but they cannot come out. Okay, that exactly is what these free electrons are to that metal lattice. So the number of free electrons is very large. But they are still bound to nucleus or still bound to lattice. So what do we call these free electrons as? We call them conduction electrons. So these are responsible for the conduction of electricity through the metal. So if you apply potential difference between ends of the metal wire, electric current will flow. Okay. Now what is work function then? We just now said that we cannot just, if even although the electrons are free, we cannot bring them out of the metal surface with our hands. Okay. But there is a technique to do that. Okay. And because these electrons are bound to the metal lattice, it means we need to supply energy to them. Okay, we need to supply energy to them, and that energy is called as work function. So what is work function? Work function is the minimum energy required for an electron on the surface of a metal body or of a metal object to come out of it. Is it clear what work function is? Work function is actually energy. What kind of energy? The energy required to pull the electron out of the metal surface. Minimum energy. That is known as work function. Because these values are so small, we don't measure them in joules anymore. We instead measure them in electron volt. So how much is 1 electron volt equal to in joules? Numerically it is the yes, negative 90 joules. Okay, this is the connection between two units of energy. So this is work function, and this is what we have observed experimentally. Okay, this is what we have observed experimentally. There is a table in your book 11.1, and as per the PDF that I have, it has been omitted for this year, so I'm not covering that table. It just has a list of different metals, different objects, or different materials, sorry, not objects, different materials, metals, and then their work functions. So for gold it is different, for copper it is different, for iron it is different, for platinum it is different, and so on. Could be an indicator for detection of metal. Next, what are the mechanisms by which we can remove or extract electrons out of a metal surface? The first one is thermionic. Thermionic refers to the energy being supplied to the electron is in the form of heat. Energy supplied in the form of heat. That is thermionic emission. What about field emission? Can anybody tell me what exactly is this field emission of electrons? Okay, when there exists very strong electric field, then the surface electrons may come out of the metal body or metal cage, metal lattice. Energy supplied is in the form of electric field. Last, photoelectric. This is of primary importance to this chapter. So what is photoelectric effect? The energy is supplied in the form of electromagnetic radiation. Note that I'm not using the word electromagnetic wave here. I'm just saying electromagnetic radiation, and that is deliberate, because wave nature does not explain this particular phenomenon of photoelectric effect. In fact, the very word photo here refers to electromagnetic radiation, okay, or light, and then electric referring to electrons. And that is our main topic of discussion for first few pages of the chapter, photoelectric effect. So let us first define photoelectric effect quickly, and then we can discuss the experimental setup. So what is the photoelectric effect? It's the phenomenon of emission of electrons from a metal surface when electromagnetic radiation of an appropriate frequency falls on it. Now here the word appropriate frequency is important. Experiments have shown that no matter how strong or how intense your beam is, beam of electromagnetic radiation, if its frequency is less than a particular value, no electron will ever come out. Okay, and we give a special name to that. We call it threshold frequency, Fmin, the minimum frequency. Some cases we may use the letter nu here, nu min. What do we call it? Threshold frequency. One of the drawbacks of the wave theory of light or electromagnetic radiation is that it doesn't predict existence of any such threshold frequency. It just says your beam is intense enough, you should see the photoelectric effect. Acha. So what is this experimental setup of photoelectric effect? You will only come to know that the electrons are being emitted by that surface if you have some mechanism to detect those electrons and the best way to detect those electrons is applying electric field and letting the electrons complete the electric circuit, so that you can also measure electric current, okay, and also potential difference. So the setup looks something like this. You have a glass tube, evacuated glass tube, so that the emitted electrons can safely reach the other electrode. Okay, this is the cathode and this is the anode. Okay, now there is a quartz window through which the electromagnetic radiation can fall on the photosensitive plate. Photosensitive plate refers to the metal plate which can emit electrons. It's a clean surface, can emit electrons when electromagnetic radiation falls on it. Correct? Okay. So how many parameters are there? Okay, in this case, the number of electrons are there, the speed of electrons with which they come out. We have found that for every electron that speed is the speed will be different. And then the third parameter is the potential difference between the two electrodes. Okay, the potential difference between the two electrodes. This actually helps us in controlling the electrons which reach, or controlling the energy of the electrons which reach the anode. And then we can define terms like stopping potential and other things. Okay, so we have a micro ammeter here which can measure the current. We have energy source here. This energy source is only to accelerate or decelerate the electrons. Please note that. This energy source doesn't have enough potential to actually remove the electrons and send them to the other end. So the role of this battery is only to accelerate or decelerate these electrons. Correct? But the main thing of knocking the electrons out of the surface, that is done only by the electromagnetic radiation. Achha. Now what is the role of commutator? The role of the commutator is to reverse the polarities. Okay. Now all of us know that electrons always move from negative potential to positive potential. Do you know that? It's contrary to what we think. We think in terms of positive charges. Positive charges, okay, always move in the direction of electric field. But for electrons it is the opposite. Electrons always move in the direction opposite to electric field. I hope you know that, right? Electrons? Yes, yes. So if you reverse the polarities and if you now increase the value of the potential, then you can actually stop the electrons reaching the other electrode. Okay? So if you apply a very strong electric field in this direction, can you tell me whether the electrons which come out of this particular plate, will they get accelerated or will they get decelerated in this case? Accelerated, because they are moving against the electric field. So if you now reverse the polarities with the help of a commutator, and if you now apply the electric field in this direction, then the electrons will be decelerated. Then they have to overcome this opposing Coulomb force of repulsion. Okay, so then we can measure the current. We can see the current decreasing as we increase the potential, and after some point the electric current will stop, which means the electrons are not able to reach the other electrode, and that value is called as stopping potential. So we'll come to that later. But have you understood the experimental setup? In your paper they might ask you to draw the figure and explain everything. What is the role of the window, why do we need an evacuated glass tube, what is the role of commutator, and so on and so forth. Is that clear?
Quartz window का वापरता है?
Well, I guess it's for plain polarized light. Yes, it's for plain polarized light.
आणि बाकीचे tube like glass as in transparent glass की like black opaque?
Yes, but the main purpose of glass tube perhaps you might get to see what's happening inside. You may see some sparkling here at this end. Transparent, but I'm not very sure about it. It's a good question. But anyways, if we had metals emitting photoelectrons with visible light, things would have been very different from what they are right now. Right? Yes. And the purpose of creating vacuum inside is air molecules should not collide with these emerging electrons. Okay. Achha. So this is experimental setup of photoelectric effect. Now let's move on to observations. As I discussed earlier, there are multiple quantities involved. Okay, can have the metal itself, you can change the metal, you can change the intensity, you can change the frequency, and also you can change the potential difference between the emitter plate and the collector plate. Emitter is the cathode and the collector is the anode, correct? So in order to study the observations or if this whole photoelectric effect, we are forced to keep varying only two quantities and other quantities as constants. So here we are not changing the material of the emitter plate, and also we are keeping the potential difference between the plates as constant, and we are also not changing the frequency. And if you now observe the variation of photoelectric current with intensity of light, okay, intensity of the light that falls on the emitter plate through the quartz window, what do you see? You see a linear relationship. Okay, you see a linear relationship. Okay, and the graph passes through origin, so this is very much like y is equal to mx. But on y-axis here we have intensity, then here, this is the slope of the line, and let me use small I here. Electric current is equal to the slope into intensity I. Okay, so what electric current small I, intensity capital. Now this can only be seen provided frequency is greater than threshold frequency or equal. Correct, we didn't mention that point quantitatively, but now I'm stating it here. For the photoelectric current to begin, you must have the frequency of incident light to be greater than that of threshold frequency. Have you understood this graph? Yes? ओजस कळा था ना? ठीक है. Okay. Graph number 2. Again, we are on y-axis we have photoelectric current or photocurrent, and on the horizontal axis we have collector plate potential. Okay, on this side we have collector plate potential. Now, the positive values of the collector plate potential mean that collector plate is at a higher potential than the emitter plate, and that's what we want. Okay, isn't it? That's what we want. Because if electric field is in this direction, wait. Okay, what I want to say is or convey here is this: positive collector plate potential means, okay, suppose this is emitter and this is collector. If we want the collector plate to be at a positive potential, it means that the electric field is like this. This is the first quadrant of the curve of the graph. So here the potential is actually helping the electrons accelerate. So we would now like to see that if we increase the collector plate potential, or if we continue to increase, do we get to see photocurrent increase? Okay, because well, they are assisting the electrons, isn't it? The potential is assisting the electrons. What we find the following. Let us keep the intensity fixed and increase the collector plate potential. What we observe is, after some point, the photocurrent does not increase, it saturates. The photocurrent saturates, and that saturation can be seen by this flattening of the curve. If we increase the intensity, yes, there is more photocurrent, but again it reaches a saturation value. If we further increase our intensity and then keep on increasing the collector plate potential, what you find is that the photocurrent will be greater, but again it is going to saturate after some time. Is that clear? We have now explained this part of the curve. ह्याच्यात काय डाऊट आहे? काय समजलं नाही ते? नाही, आत्ता आपण ग्राफचा फक्त फ्लॅटनिंग वाला पार्ट एक्सप्लेन केला आहे मी तुम्हाला. तो फ्लॅटनिंग वाला पार्ट आपल्याला असं सांगतोय की आपण जर इलेक्ट्रॉन असिस्टिंग फील्ड लावलं, इलेक्ट्रिक फील्ड, तरी इलेक्ट्रिक करंट एका पर्टिक्युलर व्हॅल्यू नंतर वाढू शकत नाही, फोटो करंट. जर आपण इंटेन्सिटी वाढवली इन्सिडेंट बीमची कुठल्या इफ या इन्सिडेंट बीमची इंटेन्सिटी वाढवली तर वाढेल, पण तो वाढतच राहणार नाही, तर फ्लॅट होईल. ते आफ्टर सम टाइम द सॅच्युरेशन करंट विल बी देयर. Even if you then further increase the collector plate potential, you will not get to see an increase in the photocurrent. It will saturate. Clear? Okay. Okay. Now let us come to the intersection of the three curves with vertical axis. Okay. What does this intersection tell you or tell us? The intersection here tells us that even if there is no electric field between the emitter and the collector, even if there is no electric field between emitter and collector, some electrons have sufficient energy to reach the collector, right? When you are in the first quadrant, it is telling you that, oh okay, electrons are actually getting help from the electric field. But when you make the collector plate potential 0, which means there is virtually no electric field between emitter and collector, there is no electric field here, but still you detect photocurrent. Okay, your micro emitter here that you have installed, it will show some deflection, which means electrons will have enough energy because the frequency is greater than the threshold frequency. They come out, they'll still have some energy, kinetic energy, they'll reach the other end. Is that clear? The intersection here, what does the intersection tell you? Yes or no? Okay, so let me just quickly write it there. Intersection of blue curves, intersection of blue curves with a vertical axis signifies that photoelectrons gain energy which is sufficient to reach the collector plate. Okay, which is sufficient to reach the collector plate. Now let us बोल.
जे इंटरसेक्शन आहे तिथे एमिटर प्लेट आणि कलेक्टर प्लेट मधला पोटेन्शियल 0 होता का?
हो.
तरी photocurrent still exists.
Because photocurrent, I mean the emission has nothing to do with the potential. The photo emission has something to do with the intensity and frequency of the incident radiation. Even if you just remove this part, okay, or basically even if you remove the battery and you just have micro emitter here, it will still show current because your frequency is greater than what? Threshold frequency. Correct? So the role of potential difference will now become clear when we go to the second quadrant. In the second quadrant, what do you see? The three curves appear to merge at a single point. Okay, the three curves appear to merge at a single point. Let us now try to understand what that particular value of potential might tell us or might be telling us. Note that we have now crossed the origin and we are now on the negative part of the horizontal axis, isn't it? So this basically tells us that the direction of the electric field has now reversed because collector is at a lower potential. So what is the direction of electric field now? This one. Is that clear? In the second quadrant, in the second quadrant of the curve, what is happening? Emitter is at a higher potential. Yes or no? Yes, yes. So electron's journey from emitter plate to collector plate will now be opposed, okay, by the Coulomb force. So only the most energetic of all will make it towards the collector plate, and that's the reason you see that the photocurrent is decreasing. The decrease in the photocurrent at the same end, you can now take any intensity curve. Okay, let's take I1. You see that the photocurrent is decreasing, the curve is dropping down. What's the reason? The reason is that some of the electrons will not be able to make it towards collector because they don't have enough energy. Some of their energy is spent in overcoming the externally applied opposing electric field, and it's this electric field which allows us to define a quantity called stopping potential. Is that clear? And that's the role of the battery here. The role of the battery in this figure is not to generate photocurrent. Okay, it is just to measure some other parameters. Photocurrent is whole and sole the job of incident electromagnetic radiation. Okay, so why do we call it stopping potential? We call it stopping potential because it stops the most energetic electron or electrons reaching the collector plate. So photocurrent goes to 0. Have you understood this? Okay, please note. Now, why can we then say that Ke max is equal to EV naught? Remember, in our second chapter, that is electric potential and capacitance, we have learned that if there exists a potential difference of V naught, okay, then what will be the electric potential energy that a charge will gain through once we send it through this? The energy will be charged into that. You know that will be the change in the electric potential energy of the charge. So this EV naught is or should be or has to be equal to the maximum kinetic energy that our electrons possess. Why am I using K max? Because only the most energetic of electrons will still be making it even if the collector plate potential is not in favor of them. Correct? So at this stopping potential, when photocurrent becomes 0, exactly equal to 0, that basically tells you that the electrons, they have just fallen short. They have failed to make it to the collector plate because of the retarding potential. Clear? This has nothing to do with incident radiation. Let me tell you that. There will still be photoelectrons emerging, but these photoelectrons which are emerging, they are being opposed by our negative collector plate potential. Correct? So there will still be photoelectric effect, but there will be nothing to measure it. Okay, the microammeter will not show any current because of the opposite, and that potential is the same. Okay, no matter what the intensity is, and that potential is called as stopping potential, a very apt name. I hope you understood this graph. We have split it into 3 parts and I have explained each part separately. The saturation, the existence of photocurrent with no electric field in between the emitter and the collector plate, and at the end the same value of the stopping potential irrespective of the intensity of the incident beam. Clear? Acha. Next part. Let's now talk about effect of frequency of incident radiation on stopping potential. Now please note the two quantities here, one of them is actually stopping potential, which we defined just now in our previous graph. Okay, stopping potential. So here on y-axis we have photoelectric current still, that is small I photocurrent, and on the horizontal axis we still have collector plate potential. But this time what we are doing is we are changing the frequency. Now the previous graph has told us that stopping potential V naught is independent of intensity. Stopping potential is independent of intensity because all the 3 curves which were corresponding to different intensities, they finally converge to or merge to the same value of the stopping potential or potential which we then called the stopping potential. So we now know that we need not draw curves for different intensities. So we keep the intensity and the material of the emitter plate the same. Okay, we keep the intensity constant and we also don't change the material of the emitter plate. Acha. And you also know that there is going to be saturation current for a given intensity. Okay, so this part is not of any interest right now. What is of more interest is if the intensity being constant, if we now change the frequency of the incident beam, we know that roughly greater the intensity, greater the energy possessed by the electromagnetic radiation. So we can now expect that if the frequency is more, the magnitude of the stopping potential will be greater, and that's what you see here. If your frequency is more, nu3 greater than nu2 greater than nu1, larger are the magnitudes of retarding potentials. That means the incident energy, the incident electromagnetic radiation on the photosensitive plate is imparting more energy to the photoelectrons, and therefore to stop them reaching the collector plate, the retarding potential should be greater and greater and greater. So for nu1 it is VO1, for nu2 it is VO2, and for nu3 it is VO3. What matters here is not the negative sign there, but the actual magnitude of that. Otherwise we'll say anyways negative V01 is greater than negative V02, then what are you saying? What I'm saying is the magnitude of V03 or VO3 is greater than that of VO2. Understood? The modulus. Is that clear? So this now should give you some hint regarding the photoelectric effect as explained by Einstein. It's not the intensity that decides the energy carried by the electrons, but the frequency that decides the energy carried by the electrons, photoelectrons. Next graph, at last. The graph of stopping potential against the frequency of incident radiation. Observation number 1, the graph is linear, not passing through origin. Graph is linear, not passing through origin, which means the stopping potential V0, okay, must be plus y-intercept. Should be some equation like this: y equal to mx plus c. Okay, y equal to mx plus c. We know that. In our 11th standard, we have studied such equations for straight lines: y equal to mx plus c. So here, y is the stopping potential and x is the frequency. Correct? This may be different for different metals. Rather, it is different. The linear nature is not going to change. It will still be the same, but depending on the metals, that threshold frequency might be different. I hope you understand the mathematical nature of it, the linearity. So focus on metal B graph. Okay? I will ask you, what do you mean when I say that this point lies on the graph? By that I mean the following. At a particular value of frequency, let's say nu1b, there will be some stopping potential. Let us call it V01b. Okay, now suppose you change the frequency. Suppose you change the frequency of your incident beam, and let us say you now make it nu2b. Okay, suppose you now make it nu2b, and suppose you now measure, or you now find the corresponding stopping potential. Okay, suppose you find the corresponding stopping potential. Let us now call it V02b. Now, no matter which two pairs of frequency and stopping potential you pick, you will always find the following quantity to be same: V02b minus V01b upon nu2b minus nu1b. Okay? And what is that? That is the slope, y2 minus y1 upon x2 minus x1. And that is exactly what the graph is telling you, the linear nature of stopping potential with frequency. Okay? Now I have one more question for you. Suppose we stretch these two graphs. Let us take the metal A now. Let's take the metal A graph, and suppose we stretch it backwards. Suppose we stretch it backwards. Can anybody explain what would the y-intercept of this point of this graph signify? So this negative portion here tells us that you need to have some minimum energy which corresponds to frequency to pull the electron out of the metal surface. In other words, that energy will be utilized in overcoming the electrostatic attraction or electric attraction that the electron has with the metal lattice. Okay, so this point of intersection tells us the work function of metal. Clear? Okay, so now having seen the observations, let's now qualitatively discuss why the wave theory does not explain the observations well. One of the reasons is that according to wave theory, greater intensity means greater energy. That's true. Greater intensity means greater energy. That's true, absolutely. But the wave nature also implies that it should also mean that the kinetic energy should be maximum. Okay, kinetic energy should be maximum. But what we have seen is here, the stopping potential V naught is independent of intensity. Which graph has shown us this? The three curves merging at the same point. The three curves merging at the same point, that basically proves that stopping potential is independent of intensity. Correct? Stopping potential is independent of intensity, and that was a problem for wave theory. Wave theory said greater intensity means greater kinetic energy. So V naught should be varying with intensity, but V naught is independent. It's found to be independent of intensity. We know that it depends on frequency. Correct? Okay. The second drawback is that wave theory does not say that there should be some minimum threshold frequency requirement. Wave theory just says intensity is enough. Okay, there is no, even if the frequency is small, intensity will take care of the smaller value of frequency. But that's not the case. According to wave theory, there should not be any threshold frequency, but there is a threshold frequency. No matter what the intensity is, if the frequency is lesser than that, you will never observe photoelectric effect. Last point, according to wave theory, the time interval between incidence of electromagnetic radiation on the metal surface and the emission of the photoelectron, this time difference or this time interval should be some hours. Okay, but the emission is almost instantaneous. I forgot the number, but there is some time lag of around 10 raised to negative 15 or 10 raised to negative 20 seconds. So it is almost instantaneous. Definitely not some hours. Correct? Okay. Then according to wave theory, you have continuous absorption of electromagnetic radiation, but that's also not the case. Einstein said that this energy comes in packets, and every packet is called as a quantum of energy, and the energy that every packet possesses is directly proportional to its frequency, and the relationship between them is E directly proportional to nu, and E is equal to h nu, where h is the Planck's constant. Correct? So they can ask you a theory question on this. Where does wave theory contradict with observations of photoelectric effect? The 3 points that I have highlighted should come now, should come there in your answer. Now, to explain the observations, Einstein gave his famous photoelectric equation. Okay, Einstein gave his famous photoelectric equation. So what did he say? He said that the energy absorbed by the electron, Einstein said the energy absorbed by the electron, which is h nu, will be spent in for two things. First is phi naught. Okay, what is phi naught? Work function. Work function signifies the portion of the absorbed energy which is utilized to overcome the electrostatic attraction. Okay, and then plus the kinetic energy. Okay, the excess energy will now be manifested in the form of kinetic energy of the moving electrons. Have you understood this? Okay. Do you want me to write it here? What is the purpose of work function again, or is it okay? It's to overcome. Okay, I'll write it. To overcome to overcome the electric attraction. And then the rest is in terms of kinetic. Okay, so what is the maximum kinetic energy? Maximum kinetic energy of electrons which will come out of the emitter plate will be the incident energy minus phi naught. Okay, K max is equal to h nu minus phi naught. And according to Einstein, the greater intensity, okay, greater intensity basically means more number of energy packets. Greater intensity does not mean more energy in a single quantum, but it means more number of packets. That's what greater intensity refers to. Is that clear? Yes? Is that clear? Or no? Okay, that's clear. Okay. Acha. So now, how does this explain all the observations which the wave theory couldn't or doesn't? The famous Einstein's photoelectric equation, K max is equal to h nu minus phi naught. Okay, K max is equal to h nu minus phi naught. That's the work function. First of all, it explains the independence of kinetic energy maximum on intensity by commenting that intensity refers to more number of energy packets and not the energy possessed by one single packet. It also explains the existence of threshold frequency. How does it explain this? We know that kinetic energy is always greater than or equal to 0. Okay, and the existence of work potential here proves that there should be certain minimum energy and therefore frequency associated with every metal, and that is what we call the work function. Correct? That is what we call work function. So h nu naught is phi naught, which is work function. So you don't have this energy, you can't save it. If you want to see photoelectric effect, you must spare this portion of your energy, supplied energy, so that the electron will come out of the prison of the metals. It also explains that the intensity is directly proportional to number of quanta per unit area per unit time. Okay, we'll not discuss that now, but please remember intensity varies with number of quanta. Intensity does not mean energy possessed by a single quantum will be or a single energy packet will be greater. Correct? It also said that one photon or one energy packet will interact with only one electron, and that explains the instantaneous emission because there is just a single photon electron pairing. And lastly, it also explains the linearity of V naught versus frequency curve. Okay, how does this explain the linearity of V naught versus nu curve? Remember, K max can now be equated to stopping potential multiplied by charge on the electron. So it is h nu minus phi naught, that's work potential. So V naught is equal to h upon E nu minus phi naught divided by E. Is that clear? And now for a moment, let us go back to that y equal to mx plus c equation. Where was it? Yes, right here. Y equal to mx plus c. So what is the slope? Slope is Planck's constant upon charge on electron, and the y-intercept is work function divided by the charge on electron. Now, because the slope is independent of the type of the metal or material, you see these lines being parallel. So the reason that metal A line and metal B line, they are parallel to each other, is because the slope of V naught versus frequency curve is actually the ratio of two universal constants, Planck's constant and charge on electron. Clear? Understood? And what is the work function there? Work function is phi naught upon E, and that is also the y-intercept. So y-intercept is not the work function, but work function divided by the charge on electron. So we have to multiply that by E to get the work function. So I hope I have explained everything from the photoelectric effect now. Correct? Please remember the Einstein's photoelectric equation. From that you can explain everything. Yes. Let's quickly discuss a few things about photon. What is photon? Photon is the quantum of energy. Okay? Photon is the quantum of energy or a packet of energy. Its energy is given by energy of a single photon is equal to h nu, where nu is the frequency. Speed in vacuum, speed of light, correct? Speed of light. And what is the momentum? Okay, what is the momentum of the photon? Fanga. Momentum is h nu by c. Momentum p is equal to h nu by c. Now, how does photon have momentum although it doesn't have mass? Remember, I explained you something called radiation pressure in our regular lectures. So that pressure refers to electrons, sorry, not electrons, photons having momentum, because otherwise they cannot exert pressure, isn't it? They exchange their momentum with the surface, correct? So they have momentum given by h nu by c. What about their electrical neutrality? Photons do not have any charge, so even if you send a photon through a very strong electric field or magnetic field, they are not affected. Okay, no deflections under electric field and magnetic field. So the photons are electrically neutral. What about the conservation? When you have a photon particle interaction such as photoelectric effect, there is photon and there is electron, which is a particle. Energy is always conserved. Momentum is always conserved, but what about number of quanta? May not be. Yes. Yeah, may not be conserved. In some situations, new photons may get created. In some cases, like photoelectric effect, the photons will get absorbed. Okay, next. Now let us talk about the next part. We have now discussed enough about particle nature of electromagnetic radiation. Now let us talk about the wave nature of matter. So the Broglie wavelength. It is a matter of or a topic of separate discussion as to how do we bring in symmetry in physics. Okay, but let's now just say that symmetry works well. Remember, in explaining the displacement current, we have invoked symmetry. We have replaced the electric and magnetic field equations, if you remember their positions. Anyways, so what did Louis de Broglie say? He said, okay, if electromagnetic radiation behaves as matter or as particle, matter may exhibit or will exhibit wave-like nature. Okay, and what is the proof of the wave-like nature? Interference. Interference is a wave phenomenon. Diffraction is a wave phenomenon, and we have seen both the interference and diffraction in our previous chapter, that is wave nature or wave theory of light. So this is the photographic proof of matter waves. So particles of matter exhibiting wave-like characteristic, we call them matter waves. We will come to the wavelength of the matter wave in a while. So this photograph is the proof. Okay, so what this photograph tells you? These are photographic plates. Okay, and the dots here signify electrons. When the number of electrons is 7, the distribution happens to be totally random. But as you increase the number of electrons, you can clearly see the electrons gathering at particular places, and then the density is lesser at in between. Okay, so these are corresponding to bright fringes and these are corresponding to dark fringes. Correct? That is an experimental or photographic proof of matter waves, or the fact that particles also exhibit wave-like characteristics. And there is a formula. We have derived this formula in our regular lectures. This is to calculate the de Broglie wavelength of an electron. If an electron is accelerated with a potential difference of v volts, then its wavelength in nanometers is 1.227 upon root of v. What is the main formula? The de Broglie wavelength is h by p or h by mv. This is the main formula, remember that. Okay. Let's now talk about uncertainty principle. Okay, let's now talk about uncertainty principle. Well, just a minute. I just wanted to tell you something. Had it. Okay, let me recall. Okay, yeah. This is what I wanted to explain. Interference, and then the matter waves also exhibit diffraction. But the experiment proving that electrons diffract has been omitted, so I'm not discussing that. That is the Davis and Germer experiment. We have discussed that in our regular lectures anyways. Achha, that's what I wanted to convey. Okay, now lastly let's go to the uncertainty principle. Which uncertainty? The view of classical physics. The view of classical physics is that multiple physical quantities associated with a particle can be measured simultaneously. That is what classical view tells us. Can be measured simultaneously and accurately. Contrary to this, the quantum physics view is that if you go to measure one quantity, there will be some uncertainty in the measurement of other quantity. And the results are evident when you talk about a photon-electron interaction. Okay, because there will be a collision-like situation there, and if you're trying to measure something, let's say if you're trying to measure the velocity of electron, so you have to send something to electron and it needs to come back, and then that itself will actually change the momentum of the electron. Okay, so there are two things here. The first is uncertainty in momentum, that is delta p, h by lambda. So this is de Broglie formula, lambda is equal to h by p, and the uncertainty in the position, here we take it as the de Broglie wavelength of light, wavelength of matter wave. So what is delta p? Delta p is uncertainty in the momentum. Uncertainty in momentum. And what is delta x? Uncertainty in position. This is still 1D, one dimensional. Okay, this is uncertainty in location or position. Let me call it position. So you can now combine the two equations and get delta p into delta x as h, and that is what we call the early form of uncertainty principle. It has been improved and we now state it in terms of an inequality. So the uncertainty in the x component of the momentum into the uncertainty in the position, it will always be a positive number given by h upon 4 pi, where h is Planck's constant, and we have this h bar, which is h upon 2 pi. You need not memorize this because you know the value of the Planck's constant. Okay, so what does this equation tell you? This equation reveals the star, that if you try to measure position accurately, its momentum we cannot measure it accurately. Okay, The more accurately a particle's position is known, smaller delta x, greater will be the uncertainty, or less will be the accuracy in measuring the momentum. Mathematically, this occurs because smaller delta x would mean larger delta x. Correct? And also you can talk about momentum. If you measure the momentum of a particle more accurately, then greater will be its uncertainty in position. That completes our revision of dual nature of radiation and matter.